Hi guys. Today we will be continuing in the series doing challenges from coding games, and I have selected to do this one called Power of Thor episode 1. I've realized there's actually quite a number of challenges that we can do, so I might post the video a day just going through each challenge. Yeah, so let's jump right into this one. So I've already looked at this challenge, and I've actually completed the challenge already, because when I was doing it for the first time I was recording my attempt. However, a friend of mine knocked here and I had to sort of cut the video in half, and yeah, but I did complete the challenge, and I'll just be going through what I was thinking throughout the process of doing that one. Okay, so we can jump right into it indeed. So now it says your program must allow Thor to reach the light of power. Thor moves on a map which is 40 by 18, which is 40 by 18. Uh, Note that the coordinates x and y start at the top left. This means the top left cell has a coordinate of x0, y0, which is that they named it, they labeled it here nicely for us. And then the most bottom right one has coordinates 39 to 17, so this should be 39 to 17. Okay, once the program starts, you are given variables, which is the x position of the light, the y position of the light, x position of Thor, and the y position of Thor. At the end of the game, you must output the direction in which you want Thor to go. So you must tell Thor where to go using north, northeast, east, southeast, just like that. Then each movement makes Thor move one cell in the chosen direction. Okay, and then so on the previous video I didn't realize that they actually gave examples here, and that's so nice. So if Thor's here, you just tell Thor go down, and Thor goes down using south, which is S. You just tell Thor to use okay, and then just give Thor an S, and then Thor goes down. Damn. Okay, so apologies. Okay, so now I read this, and then they say the constraints are, these are the constraints, which is just keep the light source. Okay, you don't have control over the light source, but keep Thor within the map. And then when I read this the first time, it didn't make sense. The response time for the game should be 100 milliseconds, because I didn't understand how I had control over the response time. But this is just saying you shouldn't do something like time dot sleep and then 100 milliseconds. If you give it that, it won't work. Or do a for loop that does a million things. A for loop that does a million things that causes the response to be greater than 100 milliseconds. So for every 10 should be less than 100 milliseconds. Effectively, that's what they're saying. Okay, so uh, the thought process in this is we need to find where Thor is relative to the light and send him to the light. That's effectively what we should do, what we asked to do here. But I was thinking now, hypergenius, get the distance between the Thor and the light. That's hypergenius. You can use that to get the distance, so the vector distance. Yeah, I was thinking around the thought of a vector, but then if you use a hypergenius, it just gives you distance. But now there's a cool thing. There's a cool mathematical concept called tan is just the difference in y divided by difference in x, and then tan theta is difference in y, difference in x, which is what we can compute ourselves here, because we do have the difference in y from Thor to the light of power, and then x, same thing. Now, so this is what I saw. So in this sort of example, uh, you can sort of, I don't know, but you can probably see this sort of the thought process towards it. But then there's a problem here. If the difference in x, which is actually what's in this example, if the difference in x doesn't need to change, then this won't know what to do. So we can solve that. By just going try and then accept, because this is Python. Try accept. So if there's a problem here, it will execute any code that's in the except block, right? Okay, so this is the only thing in this line that can cause issues. So what do we do if this issue occurs? We know that Thor can, if that happens, Thor has only two options. Thor can either go down or go up, because those are the only options. If there's no difference in the X, then Thor can either go up or down. Okay. Okay, that's good. And then I think I can start initializing some things, which is our dy equals to Thor's position. Yeah, it's Thor's y position minus the light source's position. Yes. And then we could do the same thing with our x positions. Just copy paste. Alright, that should give us the difference between Thor's x position and the light's position, and then the y positions. Okay, but now we don't have theta. Now that's what we want to calculate. And if we don't have theta, what we can do is arctan dy dx. Arctan dy dx. Oh, okay. Arctan dy dx. And then if you want to use it on Python, you need to use this library, which is math, and they call it atan. So we're going to use atan, which is arctan dy dx. And we can just name this theta, not 0. Okay. So we have theta, but theta is in Mathtan gives it in radians. I think it's going to be easier for my brain to go convert that radians to degrees, so we can actually visualize it like sort of on the graph and on my mind. Hopefully a lot of other people feel the same, that some people wouldn't convert, but I think it's easier for me to just convert because I know degrees and I can't figure out what radians are in my mind. Yeah, I can. Yeah. Okay, so we can start the actual programming. We have our theta, and then okay, I think we can start here because that's a bit easier. How do we tell Thor to go up or go down? So if this happens, tell Thor to go up or go down. How do we do that? Okay, I'm gonna initialize something quickly. I'm gonna initialize the direction, which is the instruction we're gonna give, and currently don't give instruction. And then now we can assume. Okay, so what we can now assume, that the position of Thor is greater than the position of the light source, and then that should mean Thor must go. If it's greater, if the position of Thor is greater than the position of the light source, which means if Thor is sort of here, because the coordinate system is y that way, x that way, which is also a bit sketchy because we are used to y that way and x that way, but in this case it's the other way around. So if Thor's position is maybe here and then the light source is here, Thor must go up. We're gonna assume Thor go north. Otherwise, if dx is smaller, if it's smaller than 0, then we need to tell Thor to go down, go south. Let me stop saying down. Go south. Okay, I think that should work, and this is one of the tests that can help see if this works. Play that, and you see it does not work. Why doesn't it work? SE. Okay, so it's because of this. It's because we did not give the direction, we just gave the default one that was here. So if you say direction, we test direction and it does go up, right? Okay, well done, well done. And then we can sort of see the same kind of application if we want to go left or right? And then that happens when will we require that going left or right is if your dy, if your dy this is the same throughout the light and Thor, if your dy is equal to 0, then sort of do this kind of thing. We can sort of copy that, paste, but now indent it nicely. So I'm going to assume that Thor's position, Thor's x position is greater than so I'm going to assume Thor's x position is greater than the light's position, right? So then Thor must go west, and then otherwise go east, and that's the one that tests that condition. Let's see if it works, and indeed it does, because the program is just telling Thor go east, go east, go east. Okay, and then we can so everything else, now we've sorted out north, east, west, south. We need to sort out northeast, northwest, south, east, southwest. Okay, so how do we do that? So that will only happen if there is a theta. The position, the sort of conditions that haven't been sorted out will only happen if there's a theta, because this thing only breaks the program. You don't get a theta only if you have go north or go south, right? Okay, so if we do have a theta, we can start using theta. L if our theta is okay, so we've got I'm gonna just do a quick example. So one of the examples, easy angle. Let's see what that looks like. So it's this way. Okay, so if we have this sort of setup, we want Thor to go southwest. How do we do that? So what is the angle? Okay, we can now actually get the angle and see theta. We can sort of see what the angle is, theta, and then we check that. So I wanted to print theta, and it gives me minus 22. So that's your 0, and then because of the coordinate system, this is actually 90 degrees, because that's 0 and then 90, 180, like that. But now this is minus the minus 0 degrees to minus 90 degrees in this sort of what do they call it, this thing, Cartesian plane, and then you've got your sectors. I don't remember what these are called, but in this quadrant, yes, quadrant, the word is quadrant. So in this quadrant, it's from 0 to minus 90 degrees, and that is shown by the theta angle there. Okay, so if our theta angle is between minus 0 and minus 90, then we know we should go southwest. Okay, we can program that. We can put it in here. And if theta is less than 0 degrees, but theta is greater than minus 90 degrees, then we can do something. Then we can go direction is equal to southwest. Okay, and we can simply test it out. Southwest, he's going southwest as expected. Okay, now it fails. Why does it fail? It fails because Thor keeps on going southwest, southwest, southwest. And you get to a point here where Thor has reached the maximum of the map but can't go southwest anymore, can only go that way. Alright, so we need to take that into account. And how do we do that? Okay, so we see that as the loops go in, this doesn't get updated. This doesn't get updated. The position of Thor does change, but what's being used to compute the difference between the light source and Thor doesn't change. So that's what we need to change. We can either create a variable here to keep track of Thor's position, or we can simply just use these variables and change them relative to how Thor's position and the light's position changes. Fortunately, the light's position doesn't change, it remains the same, but Thor's position changes. I think you can see Thor's position changes, the light's position doesn't change. Okay, so we need to take that into account. How do we do that? Okay, so we can simply do this. Okay, I like starting with the Y. Let's start with the Y. Okay, we know this. Every position changes by a position of 1. Every movement changes the position by 1. But now, if Thor's going southwest, which position in the coordinate system is he going relative to Y? He's going up. So we need to just update that. Make sure the program knows Thor went up. And then same thing again in the X direction. But now in the X direction, Thor is going back. Okay. So we need to update Thor's position in the X, saying he moved minus the initial one backwards. Minus 1. Then relative to the Y1, he went forward, up. Okay. So he went south. South is positive. Okay, test that. And then you can see Thor going. It's updating, and when he reaches sort of the end point of the map, Thor starts going that way because it triggers this one. It triggers this function. Hence, it's also important to put this one first because it triggers that sort of function. Okay. And then we can now do the same thing with the other directions. We just need to know what the angle is. So we can do that. I'm going to copy this. Copy that. Aha. Nope, wrong position. Okay, I'm gonna put it in there. So now I know my southwest is fine, and then let's do our south. Okay, let's do our northwest. So northwest is when the angle is between minus 90 and minus 180. Okay, so it should be so the angle should be smaller than 90 but greater than minus 180. Okay, so that's minus 180. 180 or minus 180 shouldn't really matter. Okay, maybe it does matter, I'm not too sure now. Minus 180, so if it's smaller than minus 190, which is that way, but greater than minus 180, which is this quadrant, then it should go northwest. Then we tell Thor to go northwest, and then also update Thor's position. So now we would be telling Thor to go that way, which is minus in both X and Y. Minus in both X and Y. Okay, then let's do northwest. Nope, northeast I meant to say, because we just did northwest. Northeast is in this quadrant, so then that quadrant is, so that's 90, and then from 180, nope, from 90, positive 90 to 180. So the angle should be greater than 90 but less than 180. Less than 180 degrees. Go northeast. And then southeast. Southeast is here, which is southeast. The angle should be between 0 and 90. The angle should be between 0 and 90. So it should be less than 90 degrees but greater than 0 degrees. Okay, hopefully that makes sense. Okay, and you can run this test, and then it works. It does these tests, and then you can play all the tests. The straight line works, and you have this one, and then is the angle. Maybe there's a more optimal way of doing this, which should like sort of see the exact angle, and then go boom 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 boom, not go that way. I'm not too sure, but there should be a better way. There should be a quicker way. Yeah. Okay, so these work. You just submit and it's done. Oh, okay, so there's one that doesn't work. The down one doesn't work. The down doesn't work. North south. Submit. Down. Okay, Thor goes up when he's supposed to go down. Why is that? Yeah, okay, so this was incorrect before. Okay, let's do all the tests. Thor still goes up. Direction north. Oh no. Oh no. If dy, not dx, so if dy is smaller than 0, yes. Okay, so if a change in x is not required, then we need to look at the x. If your dx is smaller than 0, then you go up. Okay, sure. I think it should be the other way. If your dx is greater than 0, then you should go. No, should actually be this way. Let's check this. Okay, that's irrelevant. Submit. Yeah. No, I am a robot. Why do you think I'm not a robot? Okay, then it works. Yes. Alright, thank you for tuning in. Hopefully I will be continuing doing more challenges, more challenging challenges. Bye bye. Cheerio.